Everyone. Today we have the pleasure to welcome Niklas Linde from Université Lausanne.
Yeah, so thank you, David. So maybe I'd just like to start by saying that, I'm here in a community that is a bit different than my normal community. It's been very great. I really enjoyed the workshop last week. And talking with some of the people, it's pretty clear that things that are maybe obvious for me that I do in geophysics is not obvious for you because you come from a different world. So I'll start with a few, before I sort of go to the topic here, which is geophysical inversion with generative models. I'll just give some sort of relatively basic examples about what type of problems we might work on and what it might imply. So at the Newton's Institute, let's start with gravity. Here we have a relative gravimeter. It measures the relative variations in the vertical component of the acceleration of gravity. And we do this here on an island. This is Stromboli volcano. We spent sort of a month here walking around and doing measurements. And then with exact positioning, with the topography, with the bathymetry, we can do a sort of linear inverse problem and determine the distribution of the density. And we can use this for various interpretations that could be geological, related to natural hazards, for instance. Maybe some of you recognize this thing. So that's the logo for the program, and it's sort of the outcome of the work of Cedric Travelletti, who used this data to invert this data with Gaussian process models, do experimental design, and look for excursion sets, so regions where density was higher or lower than a given threshold. So that's one of the collaborations I've done with David. So that's sort of a relatively small scale. Let's go here for gravity on a larger scale. So these two satellites, they're called Tom and Jerry. They chase each other through space. This is the GRACE mission. And basically you can measure variations in gravity by very accurately measuring the separation between these two satellites, how they are changing over time in sort of a picometer scale. And then what you can do with that, that was really not the intended consequence, but the sort of success of GRACE has been by repeating the measurements every few weeks. Even if the footprint is relatively large, you can follow changes in the mass distribution. So you can see, for example, the ice sheet on Greenland disappearing, or here you see, there's no scale here, but you can basically see the drying of California from 2002 to 2014. And then with recent rainfalls, you can also see how groundwater resources recover. So that's sort of a global assessment of groundwater resources. So that was sort of what we call a potential field method. Gravity, magnetics is another one. We also use equations that are more, let's say, diffusion-like. Here is electrical resistivity tomography. So here we are at the field. So these cables have outtakes every 10 meters. We put them on a line, 500 meters long in this specific case in the Poschiavo Valley. And we use the measurements. So what we have as measurements are injection of current, extraction of current. We measure the current, and then we measure a voltage between two other electrodes. And then we do this for, let's say, a few thousands of combinations. From these data, we have basically an immersion problem. This is a nonlinear problem compared to the gravity case. And we try to infer the distribution of resistivity in the subsurface. Here, actually, what we look on is not the resistivity distribution, but it's temporal variations in the resistivity distribution due to a rainfall event. So the bluish area here, a region where a recent rain event has sort of started to fill the unsaturated rock. So that's one example. You see some of the issues here. Come back to this about misspecified problems. But you see here all the topography, a lot of heterogeneity. There's a lot of geological heterogeneity here. We have a profile on one line, and typically what the model will try to do, it will try to determine the resistivity distribution with depth and along the profile, assuming that any heterogeneity that you have here just extends to infinity in the third dimension. So that's just an example of strong assumptions that are being done. Maxwell's equations, of course, also being used at low frequencies, or here at high frequencies. This is called ground penetrating radar, sort of a wave-based method. Here we are injecting salt water at 80 meters depth. There we have a fracture. when you inject the salt water will move through the fractures. The fractures have apertures of about 1 millimeter, so the separation between the rock walls is about 1 millimeter. They're connected in a network. It's very difficult to measure. With this technique, so here is being a little bit, we have 2 antennas, and we go up and down during the experiment. And what we basically observe, this would be a first example, we see basically here a response. So these are differences in the response over time. And we basically see from injection point here, the tracer has been moving up. It's an interference phenomena that allows us to use wavelengths of about 1 meter to say something about something that just have an aperture of 1 millimeter. And here was a little bit experimental design where Alexis defined, you see here a bit the problem. We inject, we do nothing for an hour and the signal disappear. This is because when we inject salt water, it's dense. So it's moving down through the system and it disappears. Here we created a neutrally buoyant tracer. This we call it wetanal. So it's a mixture of salt, alcohol, and water. So then we have density and a higher electrical conductivity. So these are just examples. Of course, you have examples that are global scale seismology. You have examples related to exploration of natural resources. But generally speaking, in geophysics, you have a lot of different designs. You do measurements on the surface, in boreholes, with a drone, with satellites, and you rely on these different types of physical phenomena to say something about physical properties at depth. So, you know, many of these things that were mentioned, maybe mostly in the talk by Jeremiah Knoblauch last week, applies here. So our forward models that we use to simulate the response of a given discretization of the subsurface are imprecise, mainly because we forget about dimensions over which properties might vary. I have this example for the resistivity, or just because of numerical errors due to spatial or temporal discretizations. We know pretty well. We get a lot of data. We are getting thousands or tens of thousands of data. So in the earth sciences, we are data rich. The signal to noise ratio is typically very high, but our likelihood functions are not necessarily, well, they're not perfectly known because these are real data. So there's some misspecification of the likelihoods. And we'll talk a little bit about the prior models and some of the challenges. That's sort of the topic. Very often we have latent variable models. We don't necessarily recognize them as such in the geophysics community, but basically we are measuring a response that depend on the source and some physics and the physical properties of the subsurface. But what we're interested in is not necessarily those physical properties, but is some derived, some related property. For example, I mentioned the question of soil moisture. Do we have water in the subsurface or not? We don't measure that, but given that the soil moisture will affect electrical conductivity, we can do. So we have some data. The subsurface is extremely heterogeneous. Permeability, so that's the main transport property related to transfer in the subsurface, varies by, at least you would say, probably 10 orders of magnitude, maybe even more. Electrical conductivity is similar. And you're interested in 3D spatial fields. Sometimes they are evolving in time. And the scales, for very sort of shallow scales, that might just be a centimeter in the surface, down to sort of the scale of the whole Earth. And we want to have some uncertainty quantification. And as I said, we have a lot of different types of data measured in different ways. So there's a whole sort of challenge here compared to maybe some other fields. So,
can I ask?
Sure.
I'm just interested, you made a distinction between forward models being imprecise and the likelihood of being misspecified. I wondered if you distinguish between those two things?
Sorry, could you tell me again?
Your top two lines,
yes.
Are they different things to you?
Yes, they do, yeah.
In what way?
Well, so you're of course correct in the sense that what we often do is that if we have model errors due to our physical modeling, because we don't ignore certain things, in some way we can of course cheat a little bit and try to put that a bit in the likelihood. But here, when I talk about likelihood function, I rather mean here the aspect of the actual observational noise. So what is actually the distribution of noise in our measurements? and not errors in our ability to model a given experiment. But of course, they are linked in some sense. Yeah.
Thanks. So what about the first and the third one? How are they different? So it feels like the forward model also is related to the prior.
Sorry, here?
No,
sorry.
Just the prior model.
Yeah. Well, so the prior model, I'll talk about that later, right? But that will be, how do we actually, in a meaningful way, provide a prior model that allows us to get something that is meaningful for us in the specific domain sciences, that is also agreement with the data. Maybe I missed something. Yeah, because
just to complement that,
yeah.
we've been having a lot of controversies about the word model for a long time. I think in this community, model is also used to speak about the prior parameter field.
Sorry, it's just a prior PDF. Yeah, sorry, it's yeah.
Would I be correct to interpret the first one is when you have a forward operator, you may not always evaluate it precisely, so it's like error evaluating this operator?
Exactly. Exactly. Yeah. Okay, so let's move on a bit. So yeah, so the focus here is really on how we define in some way a prior PDF. So maybe the term model here actually tend to have many usages. That's probably true. I'll talk a little bit first about Jeffreys priors, because you all know of them, and that's basically the guidance I had when I got started with this in geophysics. And then talk a little bit about how we solve these things classically, and some of the issues with those regularizations, if you take those regularization operators and you make prior PDFs out of them. Talk a little bit about how we can parameterize problem differently, and then achieve sort of a dimensionality reduction of that problem. That will be more like a modification. It's a little bit, let's say, my journey arriving to something called multiple point statistics that try to look on this thing very differently, and then basically how we've been then approaching this after sort of some struggles by using deep generative models, which is then the main example. And I will mainly show I will show different examples, but a little bit more on diffusion models, because there we have some recent results that are useful. So classically in geophysics, we solve an optimization problem. It's a deterministic, gradient-based approach. So we assume we have a Jacobian. And what we basically typically do is saying we have some objective function, there's some data misfit, there is some regularization on the model. That's typically specifying that the model should be varying, so you're penalizing spatial variations in the model typically, and then you have a weight here, regularization weight. Typically you maximize this one under the constraint that you fit the data. So that's what people normally do in geophysics. I would say 90% of the people probably, even more. You can of course deal with very big problems. The problem is basically the uncertainty quantification, and it's also, I'm going to come to that later, that the type of models, if this is reality, and you do your imaging, you get this. If you now want to look on a transport prediction from this model, those transport predictions will often be useless if you don't keep some of the underlying geological structure. So that was a bit what people did before, and me, a bit naive, starting in Lausanne around 2008, I sort of thought that, well, we have now this advanced MCMC algorithm. I was working with a colleague who developed some very nice algorithm, and I thought the problem was just computational. That's basically where I started. So we will do well here by just solving this with a Bayesian approach, because that's a little bit how it was in geophysics. Bayesian approach is the way to do it, but we cannot really do it because it's too expensive if you go back in the past. Here is what you get with the classical approach. Very simple model. This is electromagnetic problem. We have some measurements here. We have a very simple model here, a conductor, and then at depth we have a resistor, and at the depth here we have a conductor. Classical deterministic inversion, where we basically fit the data with the smoothest possible model. It's not great, right? We see a bit the conductor, we don't see the resistor below, we don't really see the, we're not really happy, and we don't have really any useful uncertainty quantification. So then, you know, this might appear a bit naive to you, but that's basically where we started. If we looked in the literature that was around at the time, a lot of the focus was on the marginal distribution of the parameters. And many people, there's a person, Albert Tarantola, who was very influential. He talked a lot about, you know, homogeneous priors, Jeffreys priors, And the argument was basically, yeah, you should not try to impose so much with your prior. So you maybe put a log uniform prior on resistivities, and we know the resistivities can vary to 3 orders of magnitude, something like this. So that's a little bit the how it was in geophysics at the time. The prior now has some issues, right? It's dependent on the discretization. So if I now refine a lot, I have, let's say, 1,000 parameters. My prior is, of course, different. And of course, if you show this to a geologist that you maybe collaborate with, the person will say that doesn't look like geology. And then people will often say in geophysics, well, we have so much data. Our data are so great. So by using enough data, the prior will not really matter, and we get results that are useful. So here we have all those data, signal-to-noise ratios are really high, and you still see here when we have this sort of uncorrelated prior, yeah, we see the conductor here a bit, we see a bit of resistor here, but it's not really meaningful from a perspective of a geologist. So then you need to put some spatial constraints. So let's just do that. Just use those classical roughness operators, but define them as a prior PDF. And then you can maybe do empirical base, so you try to determine what is an optimal lambda, as in the equation I showed before. Maybe you do hierarchical, so you say, let's try to fit also a bit the data noise in this. And you're getting something that is better. So in this sort of movie of images, you see this conductor a bit better, a bit this resistor below. And then you can say, well, still, if we're looking on the uncertainties here, so let's just look on 3 slides through the model. Let's maybe just look on the D3 here, just going down. No constraints. Well, you constrain basically the upper few meters. Everything else is very unconstrained. You constrain too much, well, you miss some of the important properties. Then people can say, you can define a better prior. Sure. One way of doing that is, of course, to say that I'm not going to do my inversion in this pixel space. So I'm going to define maybe invert for the coefficients of a Fourier transform, or here's the discrete cosine transform. Maybe I know something about the structures. I define some parameters based on that structure. And here is an experiment. This is an injection of CO2 in a small tank. It moves up and it's being stored in this area here. And then they said this is reality from this experiment. This is the classical deterministic inversion. Here is this uncorrelated case that we already saw is not really good. And then different parameterizations get reasonable estimates of the posterior mean with some uncertainty assessed to that. So that's, of course, something you can do. But in many applications, and that comes now a bit to the main part here of the talk, we have these spatial fields describing typically the main property of interest is probability. And what is actually important if you want to predict the response of a contaminant, so there are many examples like that, right? Nuclear waste could be one example, contamination of groundwater supply, seawater intrusion, and then, of course, like production of gas and oil. What matters when you want to predict, let's say, movement of a substance, let's say here from the left to the right, is actually not really the mean value. It's not really the variance. It's not really the correlation length. It's really how the low values or the high values are connected in space. So you have a sort of connectedness that really matter. And a classical sort of Gaussian process model will tend to have a good connection of the average. So that's sort of shown here. You can do some transforms, so you can have the same mean, variance, and correlation length, and you have the low values being connected or the high values being connected. And what you see, this is old work now, 2003, but it sort of made people wake up a little bit to this. If you now put a contaminant here and you let it move from this side to this side, even if the mean, variance, and correlation length are the same, for the different cases, first arrival of this nasty substance is maybe just a few days in this connected case, and it's 300 days in this sort of disconnected case, and in this sort of multi-Gaussian case, 150. Very, very big variation. It's not now definition here, do we have a double exponential or an exponential model, or should we have some more data to determine the covariance function here? It's really on a different scale. So how you can deal with that? Well, you can again come back to this idea that there's maybe some functions we can use, some sort of ready-made parameterizations like wavelets or principal component analysis or some cosine transform or something like this. But if you have these images with some connected structure, you basically break up all that connection. And if you now actually want to use it for some predictions of substance moving through the system, they will be bad. So the solution to that was a field that was sort of getting started probably 25 years ago now, called the multiple point statistics. Here the idea is very different. It's very impure from a statistics point of view, and I think David has his issues with this approach, but the idea is different. The idea is basically saying, let's have an image, a guiding image called a training image. It could be an outcrop, so, you know, a quarry, or where someone has been driving along, creating a road, and you've been cutting the sides, and you can look on this sort of geological structure. Maybe that structure has been interpreted by a geologist, so you have defined some phases, and you say that the brown areas here, the reddish areas, and so on, each of them are characterized by some statistics. And then you maybe do this in 3D. This is actually a 3D example, so this is also moving in the third dimension. It could also be based on some geological modeling geological processes. And with these type of techniques, you can play this thing that Albert Tarantola called the prior movie. Prior movie is basically saying, these are realizations that these MPS algorithms can create. If this is their training image, we can get prior realizations that look like this. And the idea of Tarantola was basically to say, if that movie that you play, if that convinces the persons that you work with, the geologist or whoever it is, it's good. And then your job as a geophysicist is basically to condition that to data. If you are, if they're unhappy with it, then you basically try to improve. And that changes a bit the discussion coming to these very smooth models I showed before. You get these very smooth models, and then people, when you work with people that are users of these models, they will either say, oh, that's reality, this very smooth model, and I'm going to treat it as reality, or people will say, it actually doesn't look like we would expect, so geophysics is useless. Here you sort of turn it around and you say a bit, you know, what type of features do you expect? And the MPS algorithm allows you to create that. From this, I think now you see the link here to deep generative models. You see that this is, of course, very similar. So a colleague of mine, Eric Lalois, suggested instead of using these techniques that have been developed in multiple point statistics, why not try to use deep generative models for that purpose? So you have these images like this, and why not, let's say, that you learn a lower dimensional latent model from a GAN or variational autoencoder with just a few parameters with a known prior, and just sample that with an LMCMC conditional to the data. And then you should be able to be within your prior, defined by implicitly, basically by this type of images, and with your data. So that's what we did. Of course, these are things that you all know, but I prefer to present it a bit like a story where things to do. So here we started with variational autoencoder. In comes our training images. It goes through this bottleneck. On that bottleneck, you impose a distribution, uncorrelated, Gaussian, and so on and so forth. You minimize the reconstruction loss, and then when you have this done, well, you can generate, and that's very quick. So now we can do inversion on Z. We can generate images. From the images, we can calculate the physical response. We can compare it with our data, and we can advance like this. And of course, now there are many applications like this. When this was done in 2017, in the field of earth sciences, we were, I think, the first ones doing that. So you can do this now cases where you have conditioning data. So you have some known points. So here is basically realizations of the training image, different, let's say, truths, ground truths with some measurements. And here are realizations then that are pretty much in agreement with this, in which we condition to point data. We can do, let's say, an inversion where we have some hydraulic data. Here it doesn't show so well, but we are maybe injecting water here. We measure pressure at these different blue locations. And then we can basically do inversion and get posterior realizations with, actually in this case, relatively low uncertainty. So it worked well. First, what we did at least could only be made to run for binary and categorical images. And everyone at that time was doing generative adversarial networks. So we moved to that. And you all know what that is. But that allowed us, again here, to use a lower dimensional latent representation for the parameters. And what we used was not the classical GAN, it's something called the spatial GAN. I'm not sure if it really helped, but the spatial GAN was basically a model in which the location of the latent variable is not just stored as a vector, but as an array. And the position, if you change in this area, you will basically, in the image, you will mainly change in the corresponding area. And that was done to hope that we would have some sort of localization. So it would be easier, we thought, to do the inversion. I don't know if it's the case. But anyway, we could do simulations now. Let's call it geostatistical simulations. Here is a fraction of the training image. Here are realizations. And compared to what people did in this field of multiple point statistics, it was better, at least equally well, good, and fast. And we can look on these things we call connectivity function. So I mentioned this thing, connectivity. What is that? Often it's defined, if you have defined an image into different different categories, the connectivity function basically describes what is the probability that two categories of the same type are connected in some way. So that's basically what is calculated. It was first called two-point cluster function by Tucato. And if we look on this and we compare it to the training image, we basically do well. At least it's not perfect, but it was still good. We could then go to more complicated models. So this is a bit like this sort of outcrops. So that's a fraction of a training image. We can get realizations that look, let's say, similar. We can look at that these two-point cluster functions look good. And we can do inversion. And here is a bit now the value. We have a 3D inverse problem. If we would solve this classically, we would have 100,000 model parameters. If we would say now that every discretized cell is the model parameter. Now with the GAN, we are down to 27. We have our data, and the data are basically what's called transient hydraulic tomography, meaning that you pump in a borehole and you measure the pressure variations at different locations over time. And that's the data you try to fit. Yes.
I have a question. Can you provide some interpretation for your latent variables?
In what sense?
I don't know. So, for example, are your latent variable meaningful from the geophysical point of view?
Well, so I think this is other people will probably be better in explaining that. For me, the only thing we have imposed is this localization aspect. And then by assessing, the only thing that we do here is saying that in some way we use this to learn this prior PDF, right? So we're saying that the information we have is from this training image. If we are able to produce realizations that honor that information, we are probably rather good. And then it also allows us to give some sort of density of that prior probability. But the latent variables themselves, they link to these properties in a very, very nonlinear way. And the problem, I come to that a bit later, at least when we were trying to train the GANs, we often have this problem that, I guess this is some sort of related to mode collapse, but what we often see is that images that actually fit the data well, and that when you create the images are very, very similar, they might have relatively separate latent distributions. So it basically means that when we are, our inverse problem becomes not unique. If you have our image related by some observations with the subsurface, we need to have that image that is good, but that image can, in many cases, not with a variational autoencoder, but with a GAN, it has a tendency with our trained models to sort of map into different areas. David?
Yes. You have one training image, and then you're using a learning set to train your generative model. So what's the relationship? Are you generating MPS realizations to feed your generative model?
So it's been done in different ways. So sometimes it was, in other cases, it was this. This is, for example, why the image I showed maybe here in the beginning, maybe here, they didn't really look very nice. There was all sort of artifacts, things being disconnected and so on and so forth. And that was partly due to the fact that we had a training image, and then we created realizations that we then used for our training that was based on MPS algorithms. So all the issues with those MPS algorithms, we sort of inherited. So then what we did later was rather try to work with training images that were sufficiently large from the beginning.
You train your generative model with some realization.
With a big training image, and then with the GAN here, it's basically we have a big training image, and then we took patches.
You patch.
Yeah. Yeah. So let's now, and then you can do other things, right? Here we come maybe to your question before about what did I mean about errors here for different things. So, of course, what we often do in geophysics is that this is the other side. If you go MCMC, right, you're not using the most advanced forward model that you might have because it's expensive. So you do something simpler. And here we add something relatively basic, where we basically say, it's called a straight ray approximation. So basically say that the energy is going to move on a straight line from the source to the receiver. In reality, it's going to bend. So the fastest path will be a bit bended. That's a bit more expensive. And if you now want to look on the model errors, so the differences in the prediction between, let's say, simple physics and slightly more advanced physics, they don't look very Gaussian. So it's difficult to do. So the idea here, this was first paper of Sheeran's thesis, is that we basically learned, here it's just, we could of course have done something else then again here, this is just a sort of multi-Gaussian model, but then we basically learn a low-dimensional representation of the model error, and then we invert jointly for a distribution of the errors in our modeling and the posterior of the properties of interest. So for example, we have this reference model, we reproduce it here, and then what we basically have, this is the errors, this is the model error for this image here, and we can basically get posterior realizations here, where we can actually be able to locate where in this sort of data space we are making our errors. So that was something that we did at that time. Now I think we would have done it a little bit differently, but the idea is basically that we try to use the capacity of these generative models to basically learn a representation of the errors in our modeling, and then we invert for it.
So that only works if you know what the truth is.
Yeah, but so
But
yeah,
in
so
fact,
exactly.
in reality, we never know the truth.
Absolutely.
And all our models are wrong.
Exactly.
So there's a model discrepancy.
Yes.
We do not know.
Yes.
And cannot.
Yes, I know.
So we knew it, we put it in the model.
Absolutely.
Can you cope with that?
No.
I don't think we can.
And I don't think many people
shame
can.
in not
No. So here it's more. Here it's more of a way. You know, there's still quite some resistance to Bayesian techniques in geophysics, and people say you should always use the more advanced approach. And what we can just show here is that if we do this type of behavior, we are getting so. Here we're using two relatively simple models because this slightly more advanced model, we can do a full MCMC for it, so we can get a posterior for it, and we can show that we basically converge to a very similar solution with some higher uncertainty. But of course, you're right. There's always, and that maybe comes a bit to the end of my talk, but this is why I'm interested to be here. Any ideas for how we can make our inferences more robust to all these sort of errors that I listed? That would be most welcome.
Because you have to be, if you've got a model discrepancy, you have to be careful not to use something like these squares or Bayesian calibration, because you don't want to minimize the distance between the data and the model, because that puts a bias in, because you haven't included the discrepancy.
Yeah. No, so I was spending the last 2 days reading this sort of, maybe not tutorial, but this 100-page thing by Jeremiah Knoblauch explaining how you should sort of avoid all these things. So I look forward to discuss that with there are also other people working on these things. So we've been doing a little bit in that area. I'm not presenting it here, but it's an interest for us. But here we're not dealing with it. Normalizing flows. Yeah, sorry.
Do you have a sense of what causes greater error in this model? Like what might sort of trigger the model to be less accurate? And is the uncertainty greater where the model is making more mistakes?
Yes. So the uncertainty, I think, would be larger. What is basically causing this thing is relatively basic in this setting. So basically, if you have here you have regions. Okay, so what we are voting for here is porosity. So that's a property of the subsurface. But basically, high porosity is slow media, low porosity is fast media. So if you have this sort of approach that will allow for ray bending, they will always be faster than the straight ray, because you will always try to avoid the slow zones. So you know that if I'm going to have some measurements in an area where the porosity is high, that's in the slow area, I know that my model will always try to underestimate my travel time. I see it actually here. If you look this on the model errors, they are very much skewed towards high values. Yeah.
So could this possibly answer that question about not having some reference truth in most other problems? Like if you can compare the uncertainty of the model to some ground truth in cases where you have it and there's a good correspondence, then
yeah.
you hope, I guess, that this.
Yeah, I think part. I mean, that's a little bit what we wrote in the discussion here, was just saying that this can also be a way of like a warning sign. You know, if you get this large inferred model errors here, and you capture some of the aspects in the type of errors you may be going to make with another approach, you know, we were also saying that it could also be a way of saying that, well, here's maybe an area where we maybe would like to use the more advanced physics, or maybe an area that we should try trust less. So, you know, we didn't do it like this, but if you would actually have, in many cases, we know in a sort of sign aspect about where we're making our mistakes, that we are, for example, overly underestimating the values or overestimating the values. So going a little bit in this direction can maybe us at least saying that in these areas where the model errors are high, even if we're getting this joint posterior, is probably also a place where don't trust those results so much. Yep.
So it sounds to me that it could be part of the, you know, like observation error, right? So if you don't quite, if the error to which you observe depends on the signal, you could include it in principle, or think how to include it in the likelihood, right? So like
yeah. So I mean, so if you have a linear problem, and if it's Gaussian, your model error is extremely straightforward. Here it's treated separately, but this is what one of the reviewers said. You know, why don't you just put that somehow in the likelihood? And he was saying, Thomas Meyer Hansen is saying, oh, you actually try to solve a more difficult problem than the actual problem. But what we thought was interesting is also that you get this imaging of where you're actually making errors in your with your model. But you're right. Yeah. So normalizing flows you are probably very much familiar with. We are using it here in a way that I think, yeah, it's slightly different than others. But I mean, as you know, you have a base distribution. You do those invertible transformations, and then you can sort of keep track of probabilities when you do so. And there's a paper by Hoffman where he basically, or they suggested that this could be something like a pre-processing step where you do variational inference with these normalizing flows to reparameterize a problem, because it was stated that the Hamiltonian MCMC that he was working with, if you have too much correlation, it's very inefficient. So he used it as a pre-processing approach. But the idea is basically, yeah, you have some variational distribution, it should be close to the posterior, and you sort of move to this posterior. Here, what we did was a little bit different. We have our base distribution here. These are the latent variables in the generative models. So this is going to be either a variational autoencoder or a GAN. And we use here the normalizing flows. So we do a variational inference of moving from the prior, that is defined now on the variational autoencoder or on the GAN, to move that into an approximation of the posterior. And the hope is that that would be faster. So we don't use the normalizing flows to parameterize our subsurface, but just to learn the mapping from a prior to posterior. So it becomes a little bit involved, but basically you have your prior, your latent prior, you have the normalizing flows, you get your variational distribution, you sample from it, you go into your generator, you generate an image. On the image, you calculate the forward response, and then you have the prior probabilities and the likelihoods, and then you iterate with some sort of stochastic gradient-based approach.
Can I ask a question?
Yes.
I was under the impression that when you do the normalizing flow, you sort of expect that you get non-degeneracy in a sense. Somehow you're looking at distributions that are absolutely continuous with respect to one another from the time.
Yeah.
But with the posterior distribution and the prior distribution, you expect the posterior to be much more concentrated than the prior.
Mm-hmm.
Is it something that you're facing in your case, or like some kind of degeneracy due to the fact that you have quite a lot of information in your data, and then the posterior doesn't live in the same place as what the prior does, in a sense?
So we've been using this for two applications. So I mean, from a theoretical point of view, I couldn't say, but this is basically how our approximation evolves as we start with iteration. This is for two of the latent variables. So we start with the prior, this is very wide, and clearly the posterior, this is the true model here. So posterior approximation here at the end lives in a very small space. So there's definitely a very, very big difference between sort of the space of the prior compared to the space of the posterior. Now, maybe we should discuss that later to understand, for me to understand what could be the issues of that. But in practice, when we were doing this, it works pretty nicely. And we see basically here is our reference model. And this is the mean of the posterior. And as we iterate, we basically go from sort of a blend model, and we sort of create this sort of structure that we want. And of course, it might appear relatively basic, maybe from your perspective, but in this field of geophysical or earth science inversion, it's very uncommon that you actually do an inversion that approaches something that I can discuss if this looks like geology or not, but now we are saying, okay, this is the geology, and you actually can condition in that way. So it's a different way of doing things. And maybe I'll show this as an example. Maybe it partly answers the question. Here is the prior. So these are the different latent variables. This is the true model that we had created noise on in the observations. And here's the full Markov chain Monte Carlo inversion. That's the green. And this is what we get with this normalizing flows. So we basically see it's not always exact, but generally speaking, there's a decent approximation of the posterior. Yeah.
So actually there is some theory that shows that certain types of normalizing flows are universal approximators. So in theory you should be able to recover any posterior.
Yeah. Exactly. Yeah.
Only like universal approximators of densities. Sure. But if yeah.
Okay. So the last thing I want to show, this is a bit, so these were a bit old things, and now I want to show some new results. This is work of Roberto, my postdoc, who started late last year. And what we do here is a little bit different. First of all, it's looking on diffusion models, and it's looking on multivariate. Here's the bivariate model. So you have some geological model, and you have some physical properties that is in some way dependent on the geology, but there's heterogeneity, and there's some spatial variability in this type of thing. So the physical properties for two types of geological properties or geological formations, there's some overlap, and there's some sort of complex histograms. So the question was, so Roberto visited, when he was a PhD student in Lisbon, he visited us, and he actually tried exactly the same thing for seismic data, and for this sort of bivariate case, with variational autoencoder and GANs. And what we just wanted to show here was also something that I think is not going to be a surprise for you, but here is a realization obtained by the diffusion model. Here's also, this is the mean of all our training examples. If you look on this sort of blue area here, you recover it. This was our training data, so it basically recovers this in detail. If you look on the distribution here of the different of the density distribution based in our training data, we see that it fits extremely well. And we have a separation here in our classes, class 0 and class 1, and the two different ranges of our physical properties. When we do this with the GAN, as we did before, we don't manage as well. We don't manage to fit all the details. And with the variational autoencoder, it's a little bit less good. So we can see that, for example, we have the KL divergence on the physical properties. We go from the sort of a decrease of a factor of 5 or so, 3 or 4, when we go with the diffusion model. Yep.
This that's all by the remark that the mean looks like variance, while you're speaking of unconditional guide.
Well, it's just because this is just related to how these training images were created by Roberto, so they are influenced in some extent to field example. So this is just inherent in the training data. So there is some not very strong. I mean, it's really not very strong compared to the real variations, but there's some inherent, let's say, non-stationarity in the image.
So it's not observation data; it's a mean. What you have here.
This is just the mean of all the training data. Yeah. And now maybe the last thing here. So this is the question. It was not clear for us when we started with this early this year to do inversion with these diffusion models, right? So first I thought we will just do something similar to before. So we do our generation, and then we have an outer loop where we do MCMC or something similar. Well, we realized that, of course, these models are relatively slow. And then we start looking on some approximations that were existing for how you can do this. And it was mentioned last week, so I will not give all the details before, but when you basically do the back diffusion or the generation, classically speaking, for unconditional imaging, you need to learn the score of the data distribution for the different times t. Many people have suggested that, well, one way of now doing it conditional is to say that you also learn a score for the likelihood. The problem is that the likelihood is intractable, because when you're at a given xt, your forward response depends on x0, and there are many different x0s that can be created from xt. And what was suggested by, I didn't give his name here, here, Shang. The most popular approach, not the most advanced approach, but by far the most popular approach in the literature has been this Shang approach, where the approximation is pretty strong. So you basically say, I'm going to estimate my likelihood by using at any t the best estimator I can get of x0 using this 3D formula, and it's assumed that there's no uncertainty in that estimation. That's basically what is assumed. So you basically get an estimation here of the score that is related to the variance in the observed data, but the fact that there's errors in x0 is ignored. It's of course known that that's not the case. There's, for example, this paper by Efron showing that the variance of this estimator grows in a defined way as a function of sigma t. Makes sense. We started implementing this, and then we started thinking that it didn't really make sense to us. And then we made some additions we didn't see necessarily in the literature, but actually there's, in this sort of machine learning literature, there's a lot of people that have done fixes to this approximation. We were just not aware of that before we had already done our own fix. But it's relatively simple. It's just saying that when we calculate our forward response, we have our estimate with the 3D formula of x0 hat, and then there's some additional error. How big is that error? Well, we can learn that through our training procedure. So we learn it during the training. If we want to apply this to a nonlinear problem, we basically need to move from noise in the data and basically account for our imaging. So that's through the Jacobian. So we have the Jacobian transposed times the times these errors times the Jacobian. So we have this additional error inflation. And here, that's just added, as you were saying before, it's just added to the likelihood. So it's just added to the likelihood. And it's updated. The Jacobian here is updated as we go along, as the image is being developed. So what we saw is that, yeah, indeed, people have been, in the last few years in the machine learning conferences, people have done very similar things. We haven't seen it for the nonlinear case. Most people are concerned with the linear case, I think, for various reasons. So it's sort of they've been doing this for the linear operator, but of course it's very similar. What I just want to show is that it actually works quite nicely. So we have seismic data on the surface. We have some boreholes. In the boreholes, we have observed the physical properties and the type of geology. So we have some well logs here. And here's the seismic data. So we have a linear problem conditioning to the well log data. We have a nonlinear problem fitting the seismic data. And what we are plotting here is a plot. If we start here from the left, this is for the linear case. The dashed line is how our approximation of the log score of the data distribution is decreasing as we progress towards smaller and smaller data noise. And what we are seeing here are for different noise scenario, it's how the score is decreasing on our likelihood. So our likelihood score is decreasing. That's with the change that we did, where we account for additional sources of errors. And this is the classical DPS approach by Zhang. You see basically what happens, of course, it's nothing weird here. These likelihood scores are just too high. And the consequence of this, if you look here on the data misfit, WRMS-E01, it means that you're fitting the data to the added noise. In this approach, where we have the simple fix, for different noise scenarios, it sort of converges nicely. Whereas in the DPS case, it overfits the data, and then it sort of get a variation. In the nonlinear case, it's similar for us. We see that we have a sort of nice convergence, whereas in this DPS approach, we get instability. And you can look on things like the KL here, for example, 0.5 for this simple fix compared to 1.3. And we can look, for example, on results now for the nonlinear case. And I think this is maybe what I wanted to say, is that doing a normal MCMC here with something like preconditioned Crank-Nicholson, it just doesn't converge. So Roberto was running this for ages, and it was not even close to converging. So it's not an easy problem to solve from a classical MCMC, because I said we should do a comparison. For the linear case, it works. And we see that with a simple fix, we get very similar estimation as we get with an MCMC. But here for the nonlinear case, we didn't manage to have that converging for the MCMC. And what you basically see is that this sort of DPS approach, it will underestimate uncertainty and lead to bias. You see it maybe best here. These are the geophysical data in one of the boreholes, and here's the estimates with this DPS approach. And this, with this very simple fix, we are better uncertainty and a better, let's say, we are sort of on top of the data. And we also see that on the data residuals and so on and so forth. So from a sort of purely applied perspective, this is pretty nice for us. We are getting posterior realizations that we sort of believe in. We are fitting the data well, and we avoid a bit this bottleneck of the simulations being very slow with the diffusion models, because we actually do the conditioning or the inversion during one generation step instead of having sort of an outer loop as we were doing before. So there are things to do, and of course it's not, I mean, I've seen in the literature, of course, that there are people like SMC approaches and MCMC approaches that uses this type of approximations, like this Zhang approximation, for example, and it's used as a proposal within an MCMC or within an SMC to do things even more purely. But from a practical point of view, it means that we can deal with relatively complex problems with quite some heterogeneity, quite some data, and we are getting things that, at least from our perspective, looks good. So yeah, the prior again now, I didn't write prior model this time, but basically how we are describing what we think we know about the subsurface, it's a challenge for us, it's a challenge for you, but it's even more a challenge for us. Because if you want to be really restrictive in saying that we can only know that our prior, whatever, electrical conductivity is between this value and this value, or it's just positive. Whatever images we're getting from all our data, they are really not useful. Of course, if you take the posterior mean, they look pretty much like this sort of smooth deterministic images you get. So the posterior mean are good, but the realizations are not useful, especially not for sort of downstream tasks when this is going to be used for environmental impact assessment or something similar. These deep generative models have been attractive for us because you learn this lower dimensional manifold, you can do inversion on it, you can try and assess for relatively complex scenarios. We saw that, and again here, that's of course known for other tasks, but for us the diffusion models really outperform what we could do with the variational autoencoder and GAN. And it's the same person, is Roberto, trying to do this 3 times for different networks, so it's sort of a pretty fair comparison for us at least. And then when you do this nonlinear diffusion posterior sampling, it already shown to work relatively well in the past. When we make these additions, it works better, it's more stable. And we have indeed some very strong assumptions we're making. And this is a bit why I'm here, and I'm happy to discuss with any one of you that have ideas about how to improve things. And this is maybe, it's more for myself, but I came to the realization maybe 6 or 7 years ago that in the earth sciences and in the sort of inverse group of geophysics, there was a lot of literature and a lot of developments that were very much development by ourselves with very little sort of reading and exchange with statistics. And I think one reason for that is that it's not easy to dive into if you come more from this, let's say, physics, earth science type of background. And one thing that opened a bit my mind, this was actually this review we wrote in 2017 with David and Fabio, where, and with Arnaud Doucy as well, and my colleague James, where we tried to combine and think about uncertainty quantification in, let's say, in the earth sciences. From the, we were bringing in a bit the issues we were having, and we're talking about many of these issues about misspecification and so on. And David and Fabio and Arnaud was coming with the whole, first the literature. So, this was 2017, and I still go back and read papers from that paper, so it's just an example where I think you need this cross-fertilization. I see it's happening a bit in, in the presentation we had for Microsoft, right? That there are all these teams working together for climate modeling and so on and so forth, right? But generally speaking, not enough of that is happening. And then there's another review that is more on, it's sort of prior to this work of generative modeling, where we just talk about the need for looking on geological scenarios that are relatively complex and how we can sort of approach representing the spread in this type of models, and how we can sort of do inversion in that setting. So yeah, so that was a bit what I was hoping to present, and I see it's sort of time is over, so thank you so much.
Questions from us? There are many questions from people. Yes.
So you consider virtually every type of deep generative model, DAEs, then GAN,
Yeah.
normalizing flows, diffusion models. In general, and you've used them for different types of applications
Yeah.
mostly, but like if you were to kind of go back in time now, maybe that first application you described where you used a DAE, which of these would you now be using? Like, what are the different strengths and weaknesses of these things?
Yeah, so I didn't because I was seeing I was a bit short on time. I created this little
Okay.
summary plot there, which is, well, I think it's, I mean, since the aim for many of this type of field of research is to create things that are as realistic looking as possible when you create these sort of scenarios. I think that, and I know that with the variational autoencoders, there's been a lot of development lately. There's been people doing really much more advanced type of thing. With the generative adversarial networks, there was always this issue of training, things being unstable. So at the moment, I guess, and I mean, Roberto, who did his, in his PhD, he worked with these other approaches. I mean, he's just happy with how easy it is to train the diffusion models. So I think this is a bit how we are, what we seem to like now. And then I think the other thing that is a little bit different, I guess, but I really come to appreciate the variational approach to Bayesian inversion. So before we were always doing MCMC, and now with these normalizing flows, where you can have a relatively complex, potentially complex family of variational distribution and do optimization on that. Given that you're faster, and especially because computational time is an issue often for us. So of course that is attractive. And then given that we also do many approximations, it might be nice. And then seeing this, for example, this paper of Knoblauch, you also see that there's a lot of different things you can put instead of the KL divergence, instead of how you weight the data. So I think that could be a nice vehicle. So I think to me, I mean, for let's say for the fancy cases where we especially have many of our problems, they are multivariate, and then it really seems like these diffusion models are really nice. And then I think for inversion and speeding up inversion, I think we've done lately quite a lot of work on surrogate modeling as well, which I didn't have time to talk about. But I think this sort of combination of surrogate modeling with the variational approaches and playing a little bit with how you, what sort of weights you give into the different components is something that we definitely should do more of.
The question mark for inversion for diffusion models, is that it's
Well, so it was a bit when I was doing that at the time. I mean, there is from 2024, there is this, I mean, there's just this statement, I guess, that this approach, given that this is an intractable likelihood, even if it works in practice, many of these approaches, there's no guarantees. And then, of course, with the diffusion model, if you're now going to do the inversion within an MCMC or SMC, it becomes just computationally expensive. So I think this was a bit where it was a question mark. So it's clear that you know, for what I showed for the variational autoencoder and the GAN, okay, we're saying this is our prior, this is our likelihoods, and we can see the MCMCs converging, and we have good control. What we've been doing here with this sort of fix, yeah, we do some comparison, but we know we're making approximations. There are approximation in the score approximation. There is the approximation of the log of the likelihood score and so on. So I guess that's why it was a question mark there.
Thank you.
Yeah, thank you.